Okay, folks, in this lesson, we're going to continue to work on the properties of integrals we began to study in the last lesson. So I've brought our three facts back. You can call these rules or facts or whatever you want. Just make sure you have all three of these in your notes if you don't already. I prefer to call them facts because rules makes it sound like somebody made them up, and that's really not the case, right? These are facts that we know just based on how we've defined the integral. We know that they must behave this way. In any case, let's see what these look like graphically. If you made it through the last lesson, you're going to have an easy time with this one. So jumping straight into the problems here. So here is the type of problem we're going to run into where they give you the area between the curve and the x-axis. Remember, below the x-axis, these areas are negative, and above they are positive. So I'll make a note of that right away. And then here's the integral. So remember, these bounds tell us where to look. But this one should ring alarm bells because notice the bigger bound is on the bottom. So what we want to do is we want to rewrite this right away. So I'm just going to say that this is equal to negative, and then the integral from -5. Okay, so I want you to get in the habit of rewriting any integral you see such that the lesser bound is always on the bottom because that is your way to deal with them. Now we just have to figure out this integral and then slap a negative on it, right? So the integral, I'll shade it in, from -5 all the way to 8, right? So that's -15 plus -12 plus 8 is the integral from -5 to 8 of x dx, and I don't want to get confused by the signs here. So this is the standard integral. We're going to find this solution here, and then we're going to slap a negative on it when all is said and done, so we don't have to worry about the signs. Okay, so what do we do here? We got -37 plus 8 is -22. Okay, so that means that the integral from, let's use actually our original integral. That means that our original integral, as given with the backwards bounds, is going to be equal to +22, right? So I just slapped another negative sign on this and switched the signs. Okay, so that's a very simple example of how our properties can show up graphically. We'll do a couple more. Okay, here's another one. Notice we don't have labels in the graph, we have some givens in the text this time. And I believe we don't actually need the graph for this one even. So this says that the integral from -5 to -3 is 7, and the integral from -3 to -1 is -9. What's the integral? So that integral by our rules is just the sum of the two that we are given. Graphically, I could also write that the same way. So -5, 3 is here. So that's given as 7. And then -3 to -1 is given as. So notice this looks a lot like your original problems the first time we saw these types of graphs. So the solution is just going to be -2. We're going to add those together. Okay, so here's a similar problem to the last one. It's going to look just a little bit different though. Relies on the same fact about these integrals. So we're given now -7 all the way to 1. Okay, so I'm going to actually just highlight that. -7 to 1 is what we're given. And we know that that integral is in total -3. And then from -3 to 1 is 13. We want to know from -3 to 7. Okay, so you can see where this is going right away. We know the whole thing and a piece of it. We want to know that remaining piece. So I would say that question mark plus 13 in this case is equal to, when I add or subtract 13 on both sides, I get my question mark is -16. So I'd say that this integral from -7 to -3 is -16. Okay, so they can give you either the big integral and one of the pieces, or they can give you two pieces, and either way they're going to ask you for that third missing piece. But it relies on the same rule that we saw before. now's a great time to pause and just reflect. Like, are you with me so far? Make sure your notes are good. If you didn't follow this one or the last one, make sure to rewatch them, because we're going to move on to some kind of oddball cases that they can throw at you. This one now, a little bit different. Find all x-intercepts b for which the integral from 3 to b. Well, let's think about this for a second. We want the area between 3 and whichever bound to be 0. So positives and negatives should cancel each other out. In this case, you can kind of make some guesses. It's hard to find, right? Because negative 3 plus 5 would be positive 2, so that doesn't work. Even if I take negative 3, negative 7 plus 5, still doesn't work, right? Not equal to 0. But there is always at least one solution to this. So this integral, so what I've done is, I mean, like, even if I tried to solve this, this would be whatever the antiderivative of f is. F of 3 minus f of 3 is how I would solve that. Okay, so new property. This is obviously be the same thing. Anything minus itself is 0. So new property, when I keep these bounds the same, that integral is always equal to 0. So here's another example of a problem like that. You may be tempted, notice it's a 3 again, you may be tempted to say just equals 3 and then be done. You get this one wrong. So b equals 3 is a solution, because making the bounds the same will always make the integral equal to 0. But notice positive 4 here and negative 4 here. Right? So those two things would cancel out and be equal to 0. So b equals 3, or this would be the integral from also equal to 0. So b equals 3 or b equals 8 are both solutions here. So if you get one of these wrong, just look out for that. There's another value of b that also makes our integral equal to 0. And it's because we'd have a positive and a negative area canceling out. And then for our last two examples, I put them side by side because I want you to see the difference. They're really, really similar. They're absolute value problems. So look to the question here. Notice the difference. This one, the absolute value is outside the integral. This one, the absolute value is inside the integral. Okay, so we're going to treat these slightly different. You should remember the absolute value means always positive, right? You drop the negative. It's the distance from 0 on the number line. So this left-hand case, we'll do this one first because this one's easier. So I look for the bounds, negative 1 to 8. And then I just add those up. So I get negative 15 plus 8 minus 15. And I get what? Negative 22 inside the absolute value, which becomes a positive 22 when I take the absolute value. Okay, so that works just how you'd expect. Now, my right-hand case, I'm taking the absolute value of f, not the entire integral. Okay? What that means practically is none of these areas can be negative. So this one, if I'm doing an absolute value of f, my integral would be 11 plus the absolute value. I should write the absolute value of all of them. So absolute value of 11 plus the absolute value of negative 4 plus the absolute value of 13 plus the absolute value of 3, negative 3. Right? So essentially these areas can't be negative. So they're all positive. So 15 plus 16 is 31 would be my result. Okay, so that's the difference between these two. I would say these both behave the way you would expect, but the first case, you would have been more likely to figure out on your own. This is intuitive, but maybe there's some explanation the first time you see it. I want to show you the graph version of this right-hand case, and then we'll call it a day in this lesson. Okay, so what this inside case actually means is that I'm making all these negative pieces of f positive, so those pieces get flipped above So our actual integral that we're taking would look like this instead of our original graph. I bet you're going to cruise through these. Watch carefully for your bounds.